This time I will show you how the three kinematic equations has been derived. And we have the first equation, we have Vf equals to Vi plus At. Second equation would be distance equals to Vit plus At squared over 2. And the third equation would be D is equals to Vf squared minus Vi squared all over 2a. Okay, so let's start to derive our first equation. Now we try to draw a VT graph. And we have to sketch it. And then this one is the velocity final. And the other one would be the velocity initial. And then we have here the initial time. And then we have here the final time. Now, let's try to draw a line here. So we sketch our line. Okay, remember in our VT graph, as what we discussed earlier, that the slope in a VT graph represents its acceleration. And the formula for acceleration is simply y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And then therefore, by defining our acceleration, remember that our y sub 2 here and y sub 1 would represent as Vf minus the Vi over final time minus initial time. And then therefore this defines our acceleration. And then we could write this as acceleration is Vf minus Vi over delta t, or simply we could have here the delta t, simply we could have it as t. Okay, and then therefore deriving this equation or rearranging this equation for the final velocity, we have here, we cross multiply it with 80, and then we have here Vf minus Vi, and then transposing this Vi to the other side, we have 80 plus Vi, and then I have here my Vf. So rewriting my equation would be Vf is equals to Vi plus 80. And then we have now derived our first equation. Okay, this time let's try to derive our second equation, which is distance equals to Vit plus 80 squared over 2. Now, still we have here our VT graph, and then assuming that I have now a constant velocity and I have here my change in time. Say for example, I start with time 0 and the velocity 0. I can simply draw a square, or this may not be a square but a rectangle. Okay, and as we can observe, we have here our area. And remember, the area of a rectangle, that is simply length times the width. Okay, and length times width, it could be represented as number 1, this could be our length. Okay, so this would be our velocity times the time, and then therefore velocity times time, what does it represent? Remember before that we define our velocity, the definition of our velocity as the change in distance over change in time, or simply change in displacement over change in time. We have here our change in d, or that is displacement, that is velocity times delta t, which is Vt. The area, it simply represents the distance. Okay, so we have now here that in a VT graph, the distance is being represented by the area. Okay, now let's go back to our how do we derive our equation. So let me just erase this. Okay, So what is the shape of this graph? So the shape of this graph is like a trapezoid. Then we have here formula. And then we have here, what's the formula for the area of this? We have, remember, b1 plus b2 times the height divided by 2. By replacing it with our values, the area is equivalent to, simply we have here, we could have here the b1, we have here the vi, plus, this one would be the vf, and then the height, that would be the time, or the change in time, divided by 2. Okay, and then therefore this will now represent our distance. Okay, okay, now next, let's try to define this as d is equals to vi plus vf times t over 2. And then remember that we have here our vf, and that is vi plus at. Now I will try to replace this vf with vi plus at here. Now rewrite my equation as d is equals to vi plus at times t divided by 2. D is equals to 2vi plus at, still multiply it with t divided by 2. Then simplify, we have here 2vit plus 80 square over 2. And then let me simplify this again. We have here d is equals to 2vit over 2 plus 80 square divided by 2. And therefore I could simply cancel. And then therefore we now derive our second equation, which is vit plus 80 square divided by 2. Okay, so this time let's try to derive our equation 3. So our equation 3 would be d is equals to vf square minus vi square all over 2a. Now, let me copy this formula. This will be our main formula in order for us to derive the equation 3. So we have here d is equals to vi plus vf times t all over 2. Okay, so we have derived or defined as acceleration, we have vf minus vi all over t. And then this time, our time would be equals to vf minus vi over a. Now let's try to substitute this time here with this value here. Okay, and then rewriting now our equation, that would become d is equals to vi plus vf times the time, which is vf minus vi all over a, and then this one is all over 2. Now let me rearrange. We have here vf plus vi times vf minus vi, and then let's now multiply 2 times a, that would become 2a. And remember, in our algebra class we have here that a plus b multiplied to a minus b, this is a special product, it is a square minus b square. And then therefore we have here vf square minus vi square all over 2a. And then this now is our equation 3. Okay? Now, let me remind you about this kinematic equation. This three kinematic equation is just applicable when the acceleration is constant. Take note, acceleration is constant or not changing. Okay? So meaning to say, if the acceleration is changing, this three kinematic equation is not anymore useful. Okay? We have to use calculus to arrive at a correct answer. Now, and remember, these three kinematic equations can be replaced by G if we're talking about free fall. So if we have free fall, remember we have the value of A as negative 9.8 meter per second square. And that could be written as G. So our first equation would be represented as Vf is equals to Vi plus Gt. For our second equation, that could be represented as T is equals to Vit plus Gt square divided by 2. And for the third equation, we have D is equals to Vf square minus Vi square all over 2G. Take note that we should always use the negative 9.8 meter per second square if it is a free fall.